It is the ultimate nightmare for every system administrator, video editor, and tech enthusiast. A sudden click of death, a frozen operating system, or a flashing amber LED on a server bay signaling that your drive has permanently died. All storage hardware is bound by a single, brutal truth. Eventually, every single drive will fail. But what if your system could survive a catastrophic hardware collapse without dropping a single file or pausing your workflow? That is where RAID comes in. To understand RAID, we have to look back to 1987, when researchers David Patterson, Garth Gibson, and Randy Katz at UC Berkeley published a groundbreaking paper. Back then, the computing industry relied on SLED, or single large expensive disks. Mainframes used these massive, proprietary storage units that cost a fortune. The Berkeley team proposed a radical alternative: stringing together a cluster of cheap, consumer-grade, independent hard drives that could work together to match or beat the mainframe's capacity and speed. Today, the I in RAID stands for independent. At its core, RAID is an abstraction and storage virtualization technology. It takes a collection of physical, separate drives and binds them into a contiguous logical unit. Your computer's operating system doesn't see 4, 8, or 16 individual disks formatting across separate drive letters. It just recognizes one massive unified volume, while a specialized storage controller manages how data is written underneath. We deploy RAID to solve specific storage limitations, anchored by 3 major pillars. The first pillar is performance. A single drive is restricted by its mechanical bus or flash controller speed. RAID splits your files across multiple channels simultaneously. This parallel processing scales up your sequential throughput for transferring massive video files, while drastically multiplying your random IOPS, allowing your system to process thousands of microscopic data transactions simultaneously. The second pillar is fault tolerance and uninterrupted system uptime. In enterprise infrastructure, server downtime translates directly to lost revenue. Redundant RAID levels introduce mathematical safety nets. If a hard drive mechanically seizes up, or an SSD controller fries itself, the system continues running perfectly. The users connected to the server won't experience a single hiccup, preserving data access while the hardware problem is resolved. This brings us to a critical mechanical advantage: hot swapping. In a properly configured system, you don't need to shut down the computer, unscrew the case, and reboot to fix a failed disk. You simply walk up to the storage array, pinch the latch of the dead drive, slide it out of the live chassis, and pop a brand new replacement drive back into the slot. The controller detects the new hardware and begins servicing it immediately, without a single second of system downtime. The third pillar is sheer capacity consolidation. Managing large-scale datasets across dozens of separate disconnected drives is a system administration nightmare. RAID simplifies your storage architecture. It rolls multiple physical assets into a massive, scalable storage pool. This makes it incredibly easy to configure local network directories, map user permissions, and scale out directory volumes without worrying about individual disk limits. But how does data actually land on the disks? It depends heavily on your stripe size or chunk size. When configuring an array, you define how data is carved up, typically into blocks ranging from 64 kilobytes up to 512 kilobytes or higher. Small chunk sizes are optimized for random I/O workloads, like databases, because files are distributed tightly. Large chunk sizes excel at sequential operations, allowing large media files to stream seamlessly across the array. To execute these complex data layouts, you need a controller. The traditional enterprise choice is hardware RAID. This utilizes a physical, dedicated PCIe expansion card featuring its own specialized processor and discrete cache memory. Because the hardware card handles the heavy XOR mathematical equations required for data redundancy, it isolates the storage workload completely, sparing your server's main CPU from handling any storage processing overhead. Enterprise hardware RAID cards also offer an invaluable safety feature: a battery backup unit, or flash protection module. If the data center suddenly loses power while data is sitting unwritten in the high-speed cache, the battery keeps the onboard memory powered up until energy is restored. This prevents a disastrous event known as a write hole, where partial data writes corrupt the entire volume. On the other side of the spectrum is software RAID. Instead of buying a costly hardware card, the storage array is managed directly by your operating system, using your system's main CPU. While software options were historically slow, modern multi-core processors are so powerful that software architectures like ZFS, Unraid, and Linux MD RAID are now dominant. They offer incredible flexibility, disk-type mixing, and break your reliance on proprietary hardware controllers. However, watch out for a major consumer pitfall: motherboard RAID, often called fake RAID. These are the basic RAID configuration settings built directly into consumer motherboard BIOS chips. Do not confuse this with true hardware RAID. Fake RAID has no dedicated onboard processor. It is merely a firmware layer that still relies completely on your Windows or Linux CPU drivers. If your motherboard dies, recovering your data array on a different board can be an absolute nightmare. As the world transitions from mechanical hard drives to solid-state drives, RAID faces unique modern challenges. Traditional RAID controllers were designed for spinning rust and often block the operating system's trim command, which is essential for maintaining SSD health and speed over time. Furthermore, the constant parity calculations of certain RAID configurations can accelerate SSD wear by inflating your write amplification factor. Now let's break down the individual RAID levels in explicit detail, starting with RAID 0, known as data striping. RAID 0 requires a minimum of 2 drives. It alternates writing data blocks sequentially across every disk in the group. Because you are reading and writing to all drives in parallel, performance scales linearly. 2 drives give you double the speed. But remember, RAID 0 offers zero redundancy. If one drive fails, 100% of your data across the entire array is permanently destroyed. If safety is your priority, RAID 1 is the foundational answer, known as mirroring. RAID 1 takes every incoming block of data and writes an identical clone to a secondary drive in real time. It offers bulletproof fault tolerance for 2 drive setups. If a drive suffers a mechanical failure, the secondary drive takes over instantly. Read speeds are highly optimized, as data can be pulled from both disks, but write speeds match a single drive, and you pay a 50% capacity tax for redundancy. For multi-drive arrays, RAID 5 is a classic choice, requiring at least 3 drives. It combines the speed of RAID 0 striping with a clever mathematical safety net called Parity. Using an XOR logic operation, the controller calculates an algebraic shorthand of your data and distributes these parity blocks evenly across all available disks. If any single drive in the array fails, the remaining disks use the parity math to rebuild the missing data on the fly. But RAID 5 has a dangerous vulnerabilities window. When a drive fails, the array enters a degraded state. Once you insert a replacement, the system must read every remaining sector on the surviving older drives to calculate and rebuild the new disk. This intensive multi-day stress test can cause an older drive to throw an unrecoverable read error, or URE. If that happens during a rebuild, your entire RAID 5 array collapses into total data loss. To shield your system from the catastrophic rebuild failure of RAID 5, we have RAID 6. This level requires a minimum of 4 drives and utilizes dual parity schemes, often using advanced Reed-Solomon error correction codes. By writing 2 distinct layers of parity data across all disks, a RAID 6 array can comfortably survive the simultaneous hardware failure of 2 drives at the exact same time, making it the preferred safety standard for large business storage units. When you demand enterprise performance alongside zero compromises on safety, you deploy a nested hybrid configuration like RAID 10, also written as RAID 1 plus 0. Requiring a minimum of 4 drives, it mirrors data across pairs first, and then stripes your data blocks across those mirrored sets. You get the incredible read and write performance of striping combined with the fault tolerance of mirroring, all while avoiding any complex parity write penalties. In massive enterprise data centers handling dozens of high-capacity storage drives, engineers step up to RAID 50 and RAID 60. These are nested configurations that stripe data across multiple distributed parity arrays. RAID 50 combines the capacity advantages of RAID 5 with the fast transfer speeds of RAID 0. RAID 60 provides extreme defense in depth, allowing multiple drives to fail across different subgroups without compromising your network storage volume. If you are building a modern, software-defined storage server using the ZFS file system, you will encounter its direct equivalent to RAID-Z. ZFS completely redesigns traditional array limitations by integrating the file system logic directly with the volume manager. RAID-Z 1 maps to RAID 5, RAID-Z 2 maps to RAID 6, and RAID-Z 3 introduces a triple parity architecture capable of surviving 3 simultaneous disk failures while entirely eliminating the hardware write-hole vulnerability. To maximize your system's defensive perimeter, you can configure a hot spare alongside your active RAID level. A hot spare is a physical drive that sits completely idle inside your drive bay, spinning silently but containing no active data. The moment the RAID controller detects a drive failure, it immediately commands the hot spare to wake up and start rebuilding data automatically, securing your system without waiting for an IT technician to show up. We have covered massive technical ground, but you must memorize this absolute, non-negotiable rule of storage engineering. RAID is not a backup. RAID is designed strictly to protect your immediate hardware uptime against localized physical component failure. It cannot protect your files from accidental user deletion, localized operating system corruption, ransomware encryption, or a severe power surge. For true safety, pair your RAID array with the 3-2-1 rule. 3 copies of your data across 2 different physical storage mediums, with 1 copy kept completely off-site. If this deep dive clarified your storage architecture questions or saved your current build project, smash that like button right now. Drop a comment down below. Are you building a hardware array or a software pool? And what RAID level are you deploying next? Share this video with a fellow tech builder or home lab enthusiast. And make sure to subscribe and hit that notification bell so you never miss an advanced hardware deep dive. Thanks for watching, keep your data secure, and happy building.